Out there, beyond the comfort of Earth, a lone traveler from another star system is threading its way past Mars, soon to slip behind the Sun. This visitor has a name, 3I Atlas, and with it, 1,000 questions. Is 3I Atlas a comet behaving badly, or something far more deliberate? And when it vanishes behind the Sun, will the greatest secrets unfold where no eyes can follow? And most unsettling of all, is the worst still to come? If you enjoy exploring mysteries like this, please like and subscribe. Together, we will explore what scientists and daring thinkers are suggesting about 3I Atlas. We will weigh possibilities, debate mysteries, and let the unknown carry us towards sleep. Let's begin. An object streaks through our solar system at impossible speed, 61 kilometers per second. Not born of our sun, not bound to our planets. A true outsider, carrying the signature of another star. This speed alone marks it as something extraordinary. Ordinary comets tied to the sun move at far slower velocities, obeying gravity's leash. They sweep in long arcs, speeding up near perihelion, then gliding outward again. But this object, 3I Atlas, arrives carrying energy from somewhere else. Its path is hyperbolic, an open-ended curve with eccentricity far greater than 1. This traveller came from beyond our solar system, and once its passage is complete, it will leave, never to return. To appreciate its pace, consider this. 61 kilometers per second is nearly 220,000 kilometers per hour. In 1 second, it covers the distance from New York to Washington. In a single minute, it could circle Earth. The Parker Solar Probe, our fastest spacecraft, has exceeded this speed only by diving deep into the Sun's gravity well. Atlas requires no such assist. It is the raw inertia of interstellar space, slowed only slightly as the Sun tugs on it. The age of its journey humbles the imagination. Astronomers suspect it was ejected millions of years ago, torn from the birth of some distant star system. When planets form, chaotic interactions fling debris outward, sometimes with enough velocity to escape forever. Once unbound, such fragments wander the galaxy endlessly. For ages beyond reckoning, Atlas drifted in silence, frozen, anonymous, until at last its path intersected with ours. Atlas is strange, as it carries both the activity of a comet and the precision of a traveller on a curious trajectory. What sets it apart is not simply its velocity, but its behaviour. It shines with a coma, a luminous cloud of gas and dust, proof of sublimation as it approaches the Sun. This means we can watch it with instruments across the solar system, Hubble, JWST, Mars orbiters. Never before have we had such a detailed view of something born around another star. Yet the more clearly we observe, the more unsettling the questions become. Why is its orbit aligned so closely with the plane of our planets, like a stone skipping across a calm pond instead of falling at random? Why does its chemistry deviate so sharply from expectations? Why does it appear now, at this moment in history, when our telescopes are powerful enough to notice but still too limited to explain? The visitor from nowhere passes through without invitation. It does not slow. It does not linger. It is not ours to keep. But in its fleeting presence, it leaves us with a reminder. The universe is not quiet, and the boundaries of our solar system are not the boundaries of reality. Most comets tumble in at random angles. Atlas, however, glides nearly flat along our solar system's orbital plane, a trajectory so precise it feels more like navigation than chance. Normally, interstellar visitors arrive like cosmic drifters. Their paths cut across the solar system at steep tilts, slicing through the orbital highway where Earth and the other planets travel. The ecliptic plane, the broad, flat disk traced out by planetary orbits, is rarely where outsiders appear. And yet, Atlas moves in near-perfect alignment with this invisible stage, tilted by only about 5 degrees. For a fragment from another star, this is remarkable. It's as if it knew the lane to follow, cruising our system's highway instead of wandering through its backroads. Astronomers notice patterns, but they are also cautious. A low-inclination orbit doesn't automatically prove intent. After all, interstellar objects originate in other planetary systems, and if they are ejected during planet formation, many will leave their birthplaces along a similar disc-shaped alignment. Some fraction of those, by chance, will later intersect the flattened plane of our own solar system. The odds are low, but not impossible. Selection effects may also be at work. We are more likely to detect what passes through the ecliptic because our telescopes are already watching this region. Still, this explanation doesn't erase the unease. Why? Because Atlas isn't just aligned with our plane, it is threading a sequence of encounters that look almost deliberate. First Mars in October 2025, then perihelion, hidden behind the Sun, and months later, a close pass by Jupiter. To some, this resembles waypoints, as though the object were sampling the solar system systematically. Mars for reconnaissance, the Sun for energy, Jupiter for a final survey. It is geometry that feels like choreography. To put the odds into perspective, one astronomer likened it to standing in a vast open field. If someone throws a dart from a mile away and it lands within inches of your feet, you cannot help but ask whether it was random or intentional. The dart might have simply fallen there by chance, but it feels like aim. In cosmic terms, Atlas is that dart. A rare object, perfectly placed, perfectly timed. And yet, chance can play strange tricks. We know only 3 confirmed interstellar objects in all of human history: Oumuamua, Borisov, and now Atlas. That sample is too small to declare patterns with confidence. What seems bizarre now may appear ordinary once dozens or hundreds of interstellar visitors are catalogued. Perhaps many of them will glide flat across the ecliptic. Perhaps Atlas is only the first we've noticed. For now, the mystery remains unresolved. Is this path the product of natural dynamics, a relic of its violent ejection long ago? Or is it a maneuver carefully chosen, a glide designed to keep Earth's astronomers watching in awe while remaining just out of reach? A flight plan or chance? The cosmos offers both possibilities, and as Atlas drifts onward, we are left suspended between them, unsure which story the stars are telling. Atlas brushes past Mars on October 3rd, close enough for orbiters to watch. But what will those instruments see? And why does its approach feel like a rehearsal? The distance will be about 30 million kilometers. To human intuition, that sounds impossibly far. But in astronomical terms, it is strikingly close. Only 0.19 astronomical units, roughly 80 times the Earth-Moon separation. For an interstellar object, threading past Mars with such precision will be remarkable. Not a near miss, not a collision course, but just close enough for detailed observation. Almost as if Mars were a stage and Atlas had chosen the front row. The European Space Agency has prepared for this moment. 2 spacecraft, Mars Express and the ExoMars Trace Gas Orbiter, are expected to turn their instruments toward the visitor. These spectrometers, normally tasked with analyzing the Martian atmosphere, will instead examine the gases venting from an interstellar wanderer. For a brief week, Mars will no longer be the subject of study but the platform, the vantage point for an experiment never before possible. If the instruments perform as expected, they will capture spectral fingerprints of Atlas's coma. Scientists anticipate confirming the already unusual signals seen from Earth-based telescopes. A dominance of carbon dioxide, nearly 8 times stronger than water vapor. Brightness variations, sudden outbursts, perhaps even new chemical species may reveal themselves. Every bit of data will matter, because soon the object will slip behind the Sun and Earth will lose its view. But beyond chemistry, the geometry itself tells a story. Mars will be the first checkpoint in what looks suspiciously like a sequence. After October comes perihelion, hidden behind the Sun. Then, in March 2026, a close approach to Jupiter. It almost resembles a survey, systematic, patient, deliberate. Mars first, as though to practice. Then the Sun, a test of endurance. Finally, Jupiter, the great giant of our solar system. Is this pure chance, or something more? There is symbolism too. Mars represents humanity's ambition, the stepping stone to other worlds. Our probes and rovers have mapped its deserts and dust storms, searching for signs of habitability. And now, as if scripted, an object from beyond the stars will sweep past, observed not by Earth, but by orbiters we left circling the red planet. It feels poetic, almost staged, though science insists on coincidence. Still, speculation grows in the silence. NASA and ESA will publish cautious updates, careful not to overstate what they find. Yet amateur astronomers and online observers will amplify any anomaly. A flicker in brightness, an unusual jet, a faint forward glow. The story of rehearsal will spread. A trial pass, a demonstration. On October 3rd, the truth will begin to unfold. Mars will watch, and so will we. Waiting for the moment an interstellar visitor drifts across the instruments of two lonely orbiters. After that, it will vanish behind the Sun, the rehearsal complete, and the curtain rising for the next act. Late October. As the comet nears its closest point to the Sun, Earth's view will go dark. For weeks, no telescope will be able to watch, a cosmic vanishing act at the most critical moment. This phenomenon is known as solar conjunction. It is the point when an object lies so close to the Sun in Earth's sky that our instruments cannot safely observe it. The glare overwhelms detectors, scattering light across mirrors and saturating sensors. Ground-based observatories cannot point near the Sun without risking damage. Even the most powerful space telescopes, Hubble, the James Webb, will have their view blocked. From our vantage point, Atlas will simply disappear. The timing could hardly be more unsettling. Just as Atlas reaches perihelion, its closest approach to the Sun, it will slip behind this curtain. Astronomers expect the object to heat, to outgas, to reveal its most volatile and reactive materials. This is the phase when comets show their true nature, yet at the very moment of peak activity, we will be blind. For 4 long weeks, nothing but silence. Some spacecraft will attempt to bridge the gap. The ESA's Mars orbiters may still catch faint traces from their perspective, though Mars itself will soon swing into less favourable geometry. Solar monitoring craft like SOHO and Stereo might glimpse dust and broad plasma structures, but they lack the precision to resolve fine details. For spectroscopy, for chemical analysis, for close tracking of its orbit, we will have nothing. To astronomers, this blackout is maddening but natural. Every few years, planets, asteroids, and comets pass through conjunction. Observations stop. Patience is required. Yet with Atlas, the timing is peculiar. Of all the possible orbits, of all the random angles, its closest solar approach will align exactly with the weeks Earth cannot look. It feels almost too neat, as though written into the script of a play. Speculation grows in that silence. If Atlas were natural, coincidence is the easy answer. But if it were something else, something guided, then perihelion behind the Sun would be the perfect time to act. Any course change, any maneuver, any signal sent outward would be invisible to us. The blackout becomes a stage curtain, closing just as the performance begins. When it lifts in December, we will see only the aftermath. Science demands restraint. Extraordinary claims require extraordinary evidence, and so far, the data still favour a cometary explanation. The carbon dioxide coma, the strange ratios, the nickel without iron, all unusual, but not impossible to explain with natural chemistry. Still, the human mind cannot help but wonder what might occur in those unseen weeks. As late October approaches, astronomers prepare for the silence. Predictions are published. Models are refined. Observers whisper about what could unfold while our planet is blinded. The curtain of the sun will fall, and for a month we will be excluded from the stage. When it rises again, the question will not be what we saw, but what we missed. In March 2026, the object will brush by Jupiter within just 33 million miles, a meeting of giant and wanderer where gravitational tides might reveal hidden secrets. Jupiter is no ordinary waypoint. It is the largest planet in our solar system, a behemoth with a mass more than 300 times that of Earth. Its gravity dominates the outer solar system, shaping the orbits of countless asteroids and comets. For centuries, astronomers have recognized Jupiter as both protector and predator, shielding Earth from some cosmic intruders while hurling others inward on dangerous paths. When Atlas drifts close to this giant, it will pass through a field of forces strong enough to alter its trajectory in subtle ways, perhaps enough to reveal whether it is truly just a comet or something more. At 0.358 astronomical units, the encounter will not be a grazing pass, but it will be close enough for science. Telescopes in orbit around Earth, ground-based observatories, and perhaps even Jupiter's own fleet of spacecraft will attempt to monitor the moment. The Juno mission, if extended, may still be active in Jovian orbit, offering a unique perspective. Any spacecraft in the system at that time could provide valuable data, capturing the interaction between wanderer and giant. Astronomers will be watching for more than brightness and gas emissions. They will track the orbit with exquisite precision, looking for deviations. If Atlas emerges from Jupiter's neighborhood on a path slightly different than models predict, it could suggest hidden forces at play. Outgassing jets, yes, but also perhaps something more deliberate. Jupiter's gravitational embrace is an amplifier. Any subtle propulsion or control, otherwise invisible, could become detectable in the way the object responds. There is also a symbolic resonance here. Jupiter has always stood as a gatekeeper, the sentinel of our solar system. To see an interstellar object sweep past it, as if checking in with the giant before continuing outward, feels like part of a pattern. Mars, the planet of human ambition. The Sun, the heart of the system. And then, Jupiter, the Colossus. One could almost imagine these encounters as steps in a reconnaissance mission. But imagination is a dangerous tool, and science must guard against it. Still, the numbers raise eyebrows. The probability of an interstellar object threading these alignments purely by chance is small. Harvard's Avi Loeb has calculated such odds in the past, suggesting that even rare alignments deserve consideration. After all, the galaxy is vast, and chance has infinite time to play its games. By March 2026, much will have changed. Atlas will have survived perihelion. It will have passed unseen behind the sun. It will have re-emerged for renewed study in December. And then, like an actor stepping into its final act, it will cross Jupiter's domain. If anything unusual is to be revealed, whether in chemistry, in trajectory, or in behavior, this rendezvous may be the moment. A meeting of giant and wanderer, a gravitational interrogation, and perhaps, just perhaps, a glimpse of truth hidden until the very end. A normal comet breathes water vapor. This one exhales carbon dioxide, 8 times stronger than H2O. A chemical fingerprint that challenges everything we thought we knew. In our solar system, water ice is the dominant driver of cometary activity. As comets approach the sun, surface ices warm, sublimate, and release jets of vapor that drag dust outward, forming Comean tails. Carbon dioxide is usually present, but only as a secondary player, contributing bursts of activity at specific distances. With Atlas, the hierarchy is reversed. Instead of water leading the dance, carbon dioxide takes center stage, shaping its activity from afar. Astronomers are intrigued because this ratio hints at a birthplace radically different from our own system. For carbon dioxide to dominate, the comet must have formed in a colder, darker environment where CO2 could condense freely, while water remained scarce or buried. Perhaps this object was born in the outer reaches of a distant protoplanetary disk, far beyond the frost line of its native star. If so, then its very chemistry is a fossil record of another system's infancy, preserved through millions of years of interstellar wandering. The James Webb Space Telescope's spectrographs confirmed the anomaly with precision. Carbon dioxide emissions appeared strong and clear, while water vapor barely registered. This was not a question of sensitivity or error. Multiple instruments agreed. The comet was truly exhaling carbon dioxide in abundance, and that changes the way astronomers think about comets entirely. If this is normal for interstellar objects, our sample of local comets may represent only one slice of a much broader chemical spectrum. But beyond natural explanations lies the unsettling thought. Why this ratio, and why so perfectly clear? Could deliberate processes alter the balance? Some researchers speculate that industrial chemistry might create unusual signatures. Others caution against leaping to conclusions, reminding us that nature's laboratory is vast and varied. Carbon dioxide dominance may simply be a byproduct of alien conditions, not alien intent. Still, anomalies invite imagination. Carbon dioxide is not just a volatile, it is also a greenhouse gas, a regulator of climate and habitability. On Earth, it has shaped the rise and fall of environments for billions of years. To find it leading, the composition of an interstellar visitor raises questions. Is it coincidence, or does it carry deeper meaning? Could such a body act as a delivery system, carrying not only volatiles but the very precursors of planetary atmospheres? There is also the timing. The earliest detections of water activity from Atlas occurred at unusually large distances from the Sun, far beyond the point where comets typically awaken. This means carbon dioxide was active even earlier, pushing out gas and dust while water remained frozen. It is as though the object is powered by a different engine entirely, one we have rarely seen so dominant. The chemistry of Atlas is not simply a curiosity, it is a message written in frozen molecules, whispering of environments alien to us, and perhaps of processes we do not yet understand. A normal comet breathes water. This one breathes carbon dioxide, and in that exhalation lies a clue, a hint that our solar system may not be the standard template of creation, but just one variation in a universe filled with possibilities. Hubble's cameras capture an eerie light, bright, directional, and sunward. Some see dust, others see headlights. What kind of natural body glows toward the sun? For comets, brightness is usually explained by two features: the coma, which scatters sunlight in all directions, and the tail, which streams away from the sun as solar radiation pushes dust and gas outward. This geometry produces a familiar sight: comets glowing behind them, like lanterns dragged across the night. But Atlas complicates this picture. Observers describe a forward glow, a brightness that points toward the sun instead of away from it. It seems counterintuitive. Why would a natural body appear to shine against the very source of illumination? Astronomers suggest one possibility: asymmetric outgassing. If volatile material jets strongly from the sunward side, it can create plumes of dust that scatter light forward. Certain particle sizes enhance this effect, producing what physicists call forward scattering. We've seen traces of this in solar system comets before, though usually faint. In Atlas, the effect seems pronounced, enough to inspire whispers of something artificial. The shape of the glow matters. Hubble's high-resolution images show a plume extending sunward, accompanied by a fainter tail pointing away as expected. This dual geometry does not defy natural laws, but it pushes their boundaries. The forward glow's intensity and persistence suggest unusual dust properties, perhaps grains larger, more porous, or chemically distinct from those we know. Such exotic grains could alter the way light is scattered, producing the illusion of something unnatural. And yet, perception matters. To human eyes, trained by centuries of comets behaving predictably, this glow feels strange. Some describe it as a spotlight, almost mechanical. Online speculation leaps to comparisons with headlights or beacons, as though Atlas was signaling its presence. Of course, science tempers such notions with caution. Dust physics is complex, and comets often surprise us. Still, the unusual brightness keeps the idea alive. The alien hypothesis leans heavily on anomalies like this. Avi Loeb and others point to the glow as one piece in a broader puzzle. The alignment with the solar plane, the carbon dioxide dominance, the nickel without iron. Any one of these can be explained naturally. Together, they form a pattern some find suspicious. A forward-facing glow becomes not just scattering dust, but perhaps deliberate design, a cloak of cometary physics concealing something deeper. Most astronomers reject that leap. They note that the sun's radiation, the rotation of the nucleus, and the distribution of volatile ices can combine to produce unexpected plumes. Nature is inventive, and with only 3 interstellar objects studied so far, our sample is too small to define normal. What feels engineered today may appear ordinary once more visitors are discovered. Still, the forward glow lingers in imagination. It is not a smoking gun, not proof of technology, but an optical signature that keeps us watching. A comet should glow behind. This one glows forward, and in that subtle defiance of expectation, it holds us between comfort and wonder, between dust and design. Spectra reveal nickel streaming from its coma. Yet iron, its usual partner in the cosmos, is strangely absent. Nature rarely separates them, so why now? In astronomy, iron and nickel are old companions. They are forged together in the hearts of dying stars, released in supernovae, and woven into planets, asteroids, and comets alike. When one is found, the other usually follows. They exist side by side in meteorites on Earth, in the metallic cores of worlds, and in the vaporized traces of dust tails. To see nickel glowing in the spectrum of Atlas without a corresponding fingerprint of iron is not just surprising, it is puzzling. The Very Large Telescope in Chile first picked up the signature. Using high-resolution spectrographs, astronomers observed neutral nickel lines emerging clearly in the ultraviolet and visual range. Yet iron, which should have appeared alongside, was faint or absent altogether. At first, some suspected detection limits. Maybe the iron was there, simply hidden beneath thresholds of sensitivity, but repeated observations, cross-checked by multiple teams, confirmed the imbalance. Nickel was evident, iron was not. What does this mean? One natural explanation involves excitation conditions. Different elements emit light only under certain physical circumstances: temperature, pressure, radiation intensity. It may be that iron atoms require slightly different conditions to shine, while nickel was more readily excited by the environment near Atlas's surface. In this case, the imbalance could be a quirk of physics rather than a true absence. But not all are satisfied. Nickel without iron invites speculation about processing, metallurgy, on a cosmic scale. On Earth, refined alloys separate metals deliberately. In laboratories and factories, iron and nickel are divided, purified, and recombined. To find such a pattern in space tempts some to wonder whether Atlas carries material that has been engineered, not merely condensed. Could this be a fragment of something once technological? A shard of machinery disguised as stone and ice? The leap is bold, but the question lingers. Skeptics caution that extraordinary claims demand extraordinary evidence. Comets are messy. Their chemistry varies with depth, composition, and thermal history. Cosmic ray bombardment over millions of years could alter surfaces, liberating some atoms more easily than others. The observed nickel might simply come from a thin layer of altered dust, while iron lies buried deeper. Without a smoking gun, such as consistent absence across all instruments, science leans toward the mundane. And yet, anomalies accumulate. Nickel without iron joins carbon dioxide dominance, early water activity, and the forward glow as another piece of the puzzle. None individually prove anything artificial, but together, they form a pattern of strangeness. patterns invite interpretation, and interpretation invites imagination. When astronomers gaze at Atlas through their instruments, they see not just spectra, but questions. Why should nickel emerge here, glowing brightly, while iron remains in shadow? Is it coincidence, physics, or design? We do not yet know, but as Atlas continues its journey, more data will come. Perhaps iron will finally reveal itself, or perhaps its silence will deepen the mystery, leaving us to wonder what secrets this interstellar wanderer carries within. Astronomer Avi Loeb offers a framework. The Loeb scale, a way to rank interstellar mysteries between natural and artificial. On this scale, Atlas sits uneasily in the middle. The idea is simple but useful. Not every anomaly in astronomy demands an alien explanation, yet not every anomaly can be explained away as ordinary either. The Loeb scale is meant to give scientists, and the public, a language for where an object falls between the extremes. On one end you have pure natural phenomena, a comet, an asteroid, a lump of frozen gas and rock behaving exactly as expected. On the other end lies the artificial, a probe, a fragment of spacecraft, or a deliberate construction designed by intelligence. Most objects fall easily toward the natural side, but some, like Oumuamua in 2017, demand a closer look. Loeb suggests we treat anomalies not as embarrassments to explain away, but as opportunities to measure strangeness. For example, does the trajectory match expectations? Does the chemistry resemble known comets? Does the object's light curve behave like a spinning rock or like something more deliberate? By weighing each factor, we can give an approximate ranking, not proof of intent, but an index of weirdness. On this scale, Atlas is troublesome. Its alignment with the solar system's orbital plane leans it towards suspicion. Its carbon dioxide dominance makes it chemically unique. The forward glow raises eyebrows, and the nickel without iron puzzle deepens the uncertainty. Yet at the same time, Atlas behaves like a comet in other respects. It outgasses, it develops a coma, it follows gravitational mechanics to within observational limits. No obvious thrust, no narrowband radio emissions, no repeating signals. In short, strange but not impossible. That middle ground is where controversy thrives. Some scientists prefer to dismiss anomalies quickly, fearing that too much speculation risks credibility. Others, like Loeb, argue that ignoring them costs us discoveries. If humanity had dismissed pulsars as mere noise, we would have lost a key to understanding neutron stars. If fast radio bursts had been shrugged off, we would still be blind to an entire class of astrophysical events. Progress often begins in the weird. And yet, there is risk. Overstating the oddness of Atlas could fuel unnecessary fear or hype. The alien probe headlines may attract attention, but they also invite skepticism and pushback. The Loeb scale is meant as a tool to balance these forces, a way to keep conversation grounded in data while still acknowledging when an object refuses to fit comfortably in our models. On that spectrum, Atlas is neither mundane nor miraculous. It sits in the grey, defying easy categorization. For science advances not in the things that fit neatly, but in the outliers. The comet that doesn't behave, the orbit that seems too precise, the chemical fingerprint that raises questions. In the months ahead, as Atlas moves past the Sun and toward Jupiter, its ranking may shift. New data could nudge it down toward the natural, or up toward the extraordinary. For now, it remains suspended in the middle, balanced between dust and design, mystery and meaning, uncertainty and possibility. NASA and ESA issue quiet technical notes. No press conferences, no hype, just silence. Silence that feels louder than words. It is not unusual for space agencies to tread carefully with public communication. Science, after all, advances slowly. Observations are gathered, data are peer-reviewed, models are debated, and only then are conclusions drawn. But with Atlas, the silence seems heavier, almost deliberate, the most extraordinary interstellar visitor humanity has ever had the chance to study drifts through our solar system, and the official updates remain understated, tucked into obscure journals or buried within mission reports. For the public, this quiet feels unnatural. When comets streak close to Earth, when asteroids pass by safely, agencies often seize the moment to educate and inspire. Press briefings, animations, artist renderings, these are common. Technical notes confirm detections of carbon dioxide dominance, nickel emission lines, and brightness curves. Yet beyond the data, there is little narrative, no speculation, no wonder, just the facts, delivered in the plainest possible terms. Some interpret this as professionalism, an effort to avoid sensationalism after the controversies surrounding Oumuamua. Others, however, sense caution. Silence leaves a vacuum, and vacuums invite imagination. Online forums, podcasts, and late-night discussions amplify every anomaly. Why so much restraint? Why so little commentary from institutions that usually celebrate cosmic discovery? History offers context. In 2017, when Oumuamua appeared, excitement flared quickly. Media outlets declared it an alien spacecraft, while scientists scrambled to temper expectations. The backlash was sharp, and many astronomers grew wary of repeating the cycle. By saying less, perhaps agencies hope to contain speculation, to let the data speak for itself. Yet the effect may be the opposite. The quieter the officials, the louder the speculation grows. This is not to say agencies are ignoring Atlas. Quite the opposite. Behind the scenes, international collaborations are running non-stop. Hubble and JWST observation time has been scheduled. Mars orbiters will turn their instruments toward the visitor during its October flyby. Teams at the European Southern Observatory and NASA's Planetary Defense Offices are monitoring its trajectory with precision. The science is robust, the interest enormous, but the presentation remains muted. Perhaps the silence is strategic. To some, downplaying unusual results prevents premature conclusions. To others, it feels like containment, a way of shielding the public from unsettling questions. Could it be that agencies themselves are unsure how to interpret the anomalies? Or are they simply waiting, holding their voices until perihelion and the Jupiter encounter provide decisive answers? What is clear is that silence itself shapes the narrative. Each gap is filled by curiosity. Each absence of commentary is read as implication. And so, while NASA and ESA publish data in quiet tones, the world listens to the whispers around them. The object's strangeness does not fade, it multiplies in the shadows of official restraint. Silence, then, is not empty. It is a canvas on which speculation paints. Whether intentional or not, the agency's quiet has become part of the story of Atlas. And in its hush, the mystery grows louder still. As the comet nears Mars, US defense officials convene in secret at Quantico. No connection is proven, yet the timing draws attention. Quantico, Virginia, is better known for training officers, running simulations, and conducting strategic briefings than for astronomical debate. But in late 2025, as Atlas approaches its Mars flyby, reports emerge of closed-door sessions involving high-ranking defense and intelligence officials. The subject matter is never disclosed. The agenda remains classified. But the timing, so close to the comet's near pass, sparks speculation. Could it be coincidence? Or does the military see something in Atlas that demands attention? In fairness, defense institutions track space closely. Satellites, missiles, orbital debris all fall within their mandate. Interstellar objects, though scientifically fascinating, generally pose no threat. Atlas's trajectory is hyperbolic, meaning it will pass through the solar system once and depart forever. It is not on course to strike Earth. On the surface, there is no reason for the Pentagon to take interest. Yet history shows that unexplained phenomena often capture military curiosity. From unidentified aerial encounters in Earth skies to near-Earth objects, the unknown is never ignored. Some analysts suggest the gathering at Quantico may be part of broader preparedness exercises. What if an object did threaten Earth one day? What if an interstellar body carried unknown risks, radiation, unusual chemistry, or, in the most speculative scenarios, technological signatures? Quiet planning sessions could be prudent, a way to test responses before any real crisis emerges. Others, however, see a different narrative. The sequence of Atlas's encounters, Mars, then the Sun, then Jupiter, has already been described by some as resembling a survey. If agencies even faintly entertain that idea, then defense officials might feel compelled to ask, what if? What if this is not simply a comet? What if its passage offers more than just scientific lessons? What if it is observing us as much as we are observing it? Of course, no evidence supports such claims. The Quantico meetings remain opaque, and their true purpose could relate to terrestrial matters entirely unrelated to astronomy. Yet secrecy breeds suspicion. Just as NASA's silence has fueled speculation, so too does the military's reticence. In the absence of clear answers, the human mind connects dots, weaving patterns out of coincidence. It is worth remembering that extraordinary cosmic events often overlap with earthly concerns. Governments, mindful of public perception, may choose not to link the two openly. A secure briefing room in Quantico may be discussing cybersecurity, climate, or global conflicts. Yet because the timing coincides with the Mars flyby of an interstellar visitor, the imagination runs wild. The truth may be simple, or it may be more layered than we think. What matters is that Atlas, without altering its course, has already reshaped conversations far beyond astronomy. Scientists debate its chemistry. Agencies issue sparse notes. And now, behind closed doors in Virginia, officials gather under a veil of secrecy. Whether coincidence or connection, the Quantico gathering reminds us that Atlas is no longer just a comet. It is a mirror, reflecting our fears, our hopes, and our readiness, or lack thereof, to confront the unknown. Mars, the Sun, Jupiter, each a waypoint, each a place where spacecraft can observe or be observed. Does this sequence look like chance or choreography? On its hyperbolic path, Atlas will not linger. It will pass quickly, in and out of our solar system, within a span of months. Yet the sequence of its encounters feels oddly deliberate. First, a brush with Mars in early October 2025, close enough for orbiters to pivot their instruments. Then, just weeks later, perihelion, hidden behind the Sun, where Earth's telescopes will be blinded. And finally, in March 2026, a pass within 33 million miles of Jupiter, the largest planet and gravitational sentinel of our system. 3 encounters, 3 distinct stages. To astronomers, such a sequence is, in principle, explainable. Hyperbolic orbits bend naturally under the influence of gravity. Mars, the Sun, and Jupiter all lie along the ecliptic plane. If Atlas's trajectory happens to align with that plane, then planetary encounters become inevitable. A cosmic billiard game where angles and masses dictate the course. Statistically unlikely, yes, but not impossible. Still, the order raises eyebrows. Mars first, the planet where humanity has left orbiters, rovers, and dreams of colonization. The Sun next, the source of energy and life, but also the greatest shield, blinding us from observation. Then Jupiter, the system's titan, whose gravity has sculpted the fates of countless bodies. Together, they resemble checkpoints, as though Atlas is moving through a script written in advance. This sense of choreography is what fuels the more speculative interpretations. Could an object deliberately choose such a path? If it were designed for reconnaissance, these waypoints would make sense. Mars, to test our instruments. The Sun, to cloak movements from our gaze. Jupiter, to measure the system's heart of gravity. It is a pattern that, to some, feels too purposeful to ignore. yet science urges caution. Our perspective is limited by small numbers. We have observed only 3 interstellar visitors. From so few examples, drawing conclusions about patterns risks bias. Coincidences appear meaningful only because we want them to be. If future interstellar objects show similar alignments, then we may have cause to revise our assumptions. Until then, the safe explanation remains chance. And yet, chance has a way of unsettling us. The dartboard analogy returns. If you throw a dart from a mile away and it lands at your feet, you wonder whether it was really random. Atlas feels like that dart. The closer its encounters align with meaningful locations, the harder it becomes to dismiss the feeling of choreography. In March 2026, as it rounds Jupiter, we will have our clearest chance to test this question. If the trajectory deviates from predictions, if its interactions suggest forces beyond mere gravity, then the idea of planning will gain weight. If it follows the expected curve precisely, then the choreography may dissolve back into coincidence. For now, the pattern remains suggestive, not conclusive. Mars, the Sun, Jupiter, 3 encounters, woven together like steps in a cosmic dance. Whether it is a dance of chance or a dance of intent, that remains the question still unfolding. The first interstellar object baffled us with acceleration and silence. Now, Atlas arrives. Are we witnessing the sequel to a cosmic story we barely understand? When astronomers spotted Oumuamua in October 2017, it came as a shock. A faint streak in the sky, travelling far too fast to be bound to our Sun, revealed itself as the first confirmed interstellar visitor. But what followed was stranger still. Its brightness fluctuated dramatically, suggesting a shape more elongated than anything we had ever seen. Perhaps a cigar, perhaps a pancake. Its acceleration changed subtly, in ways that could not be explained by gravity alone. Yet no jets of gas were visible. It was pushing itself, but with what? The mystery deepened because Oumuamua left us so quickly. By the time telescopes had turned in full force, the object was already fading into the distance. No spacecraft could intercept it. All we had were weeks of hurried observations, fragments of data stitched into theories. Some scientists argued it was an icy shard, with exotic ices like hydrogen or nitrogen sublimating invisibly. Others proposed dust fractals, fragile structures drifting on sunlight. And then there was the bold idea. Advanced technology. A solar sail, perhaps even a probe. The debate raged, but the object itself slipped away, silent. That silence has haunted us ever since. Oumuamua taught us humility. The universe will not slow down for our curiosity. It also taught us urgency, that the next interstellar visitor must be watched more carefully, more quickly, with better tools. The lesson was clear. We needed to be ready. Now, in 2025, Atlas arrives. Unlike Oumuamua, it is not silent. It breathes. It shines with a coma and tails. It exudes carbon dioxide, spews nickel, and flickers in brightness like a living thing. Unlike its predecessor, it gives us time, months of observation, chances to track its encounters with Mars, the Sun, and Jupiter. If Oumuamua was puzzling because it was too little, Atlas is puzzling because it is too much, too many anomalies, too many deviations from the norm. The comparison between the two is instructive. One object seemed barren, quiet, almost stealthy. The other is active, noisy, dramatic. Perhaps they are two ends of a spectrum of interstellar debris, a reminder that other planetary systems can produce a staggering diversity of wanderers. Or perhaps, more unsettlingly, they represent two chapters of a story. Different tools, different designs, different purposes. The first a scout, the second a performer. Astronomers hesitate to frame it in such terms, but the echoes are hard to ignore. In both cases, chance brought us a messenger from beyond. In both, anomalies exceeded expectations, and in both, our interpretations revealed as much about ourselves as about the objects. Do we see dust physics? Or do we see intent? Do we see a rock? Or do we see reconnaissance? The lesson of Oumuamua remains: be cautious, but be open. Do not dismiss the strange. Do not leap too quickly. Watch, record, learn. For now, Atlas carries the sequel, and whether it resolves the mystery or deepens it, we are compelled to listen. Unlike Atlas, Borisov looked like a normal comet. Ordinary chemistry. Predictable behavior. So why does this new visitor feel so alien? Discovered in 2019 by amateur astronomer Gennady Borisov, the second interstellar object was immediately recognizable. It grew a coma, it sprouted a tail, and it shed gas in ways indistinguishable from comets native to our own solar system. Its spectrum revealed familiar signatures: water vapor, carbon monoxide, cyanide. In short, Borisov behaved exactly as textbooks said it should. Apart from its interstellar velocity, it could have been plucked from the Oort cloud. Astronomers took comfort in this. The galaxy, it seemed, was full of comets much like our own. Atlas disrupts that comfort. From the start, it has refused to conform. Where Borisov breathed water, Atlas exhales carbon dioxide. Where Borisov's chemistry was balanced, Atlas shows nickel without iron, strange dust scattering, and water outgassing at impossible distances. Even its trajectory is odd, gliding neatly along the ecliptic plane, weaving past Mars and toward Jupiter in a sequence that feels intentional. The contrast between the two visitors could not be sharper. Comparisons highlight the puzzle. Borisov was the control, the baseline, the reassuring normal of interstellar debris. Atlas is the anomaly, the outlier, the case that forces us to re-examine our assumptions. If all we had seen were Borisov-like objects, we might have concluded that planetary systems everywhere produce the same kinds of icy wanderers. But Atlas tells us the truth may be stranger. Diversity is the rule. Some interstellar objects may look familiar. Others may not, and in that variety lies the possibility of discovery or surprise. It is tempting to imagine that Borisov and Atlas belong to entirely different categories. Perhaps Borisov was a typical fragment, ejected in the chaos of planetary formation. Perhaps Atlas, by contrast, is rarer, born in colder, more exotic conditions, or shaped by processes we have not yet understood. The extreme dominance of carbon dioxide, for example, could point to a birthplace beyond the frost line of a distant star, in regions so frigid that water was locked away while CO2 condensed freely. That kind of chemistry would not surprise us in theory, but seeing it so vividly in practice is another matter. And then there is the philosophical comparison. Borisov reassured us. It reminded us that the cosmos often follows patterns, that interstellar visitors could be catalogued and explained. Atlas unsettles us. It whispers that the universe is more complicated, that anomalies may not always fit neatly into our models. Where Borisov calmed the waters, Atlas stirs them into waves. Scientists thrive on this duality. The ordinary gives us confidence, the extraordinary gives us progress. Without anomalies, science would stagnate. By forcing comparison with Borisov, Atlas serves its role perfectly. It tells us that one example is never enough, that 3 interstellar visitors already reveal a spectrum wider than we expected. So, why does Atlas feel so alien? Because Borisov taught us to expect the familiar, and Atlas denies us that comfort. Together, they are chapters in a story not of similarity, but of strangeness. And with each new visitor, that story will only grow more complex. As it spins, Atlas flickers. Brightness rises, then fades, almost like breathing. But is this natural or mechanical? Astronomers call these variations light curves, the way an object's brightness changes over time. By studying these curves, scientists can learn about rotation, shape, and surface features. For comets, The pattern often reflects jets of gas venting at irregular intervals, exposing icy patches that flash like beacons as the body turns. In the case of Atlas, however, the rhythm feels strangely steady, almost pulsing. The curve resembles the inhale and exhale of a living thing. The data show repeating cycles of brightening and dimming, suggesting a rotation period that is neither too fast nor too slow. If Atlas was spinning chaotically, like a tumbling shard, the curve would appear jagged, unpredictable. Instead, its brightness waxes and wanes with surprising consistency, as though governed by an underlying rhythm. This is not proof of anything unnatural, but it does raise questions. Why so regular? Why so smooth? One explanation is geometry. If the nucleus has a highly elongated shape, sunlight may reflect differently as it rotates, producing a clean, periodic signal. Oumuamua, for example, displayed wild light curve variations that suggested an elongated form. Another possibility lies in outgassing. If jets of carbon dioxide are released at fixed locations, then as the nucleus spins, those jets may light up in sequence, creating the illusion of breath. Yet the regularity continues to intrigue. A repeating light curve can, in some contexts, suggest engineered rotation, a balanced spin, carefully maintained. Spacecraft, after all, often rotate deliberately to stabilize themselves or distribute sunlight evenly across their surfaces. When astronomers see such rhythms in artificial satellites, they recognize them as signs of control. With Atlas, the same rhythm invites uneasy comparisons. Could the breathing curve be more than coincidence? Caution tempers curiosity. The human mind is wired to recognize patterns, even where none exist. A heartbeat in a signal, a flicker that resembles breath. These invite us to project meaning onto data that may be purely physical. Natural bodies can spin with remarkable regularity. Some asteroids rotate like metronomes for millions of years, their stability preserved by simple inertia. Atlas may be no different. Still, the symbolism lingers. To describe its light as breathing is more than metaphor. It is how the curve feels, a cosmic inhale and exhale written in photons. And with each cycle we are reminded of its alien origin. This is not a body born under our sun. It is a fragment from another star system, carrying within it a rhythm that has persisted for millions of years, only now passing before our instruments. Whether natural or mechanical, the breathing curve matters. It is a signal, a story told in light. And as Atlas spins on, flickering in the darkness, we cannot help but wonder. Its closest pass to the Sun falls during solar conjunction, when Earth cannot see. Coincidence or cover? Perihelion is the most revealing moment for a comet. As the nucleus sweeps closest to the Sun, heat awakens its hidden ices, releasing volatile gases in torrents. Comets grow brighter, tails stretch longer, and the true chemistry of the body comes to light. For astronomers, perihelion is the climax of the performance, the instant when the curtain should rise. Yet with Atlas, that climax will unfold behind a veil. During late October 2025, the comet will align almost exactly with the Sun from Earth's perspective. Solar conjunction will blind our telescopes, leaving us unable to watch. This timing unsettles scientists and dreamers alike. After months of anticipation, the object will slip into invisibility just as its activity peaks. Weeks will pass with no direct view. Observatories on Earth, Hubble in orbit, even the James Webb Space Telescope. All will be rendered useless. The sun's glare overwhelms their optics, washing out any trace of the visitor. It is as if the cosmos has chosen the worst possible moment to dim the lights. Coincidence is the straightforward answer. Orbital mechanics are indifferent to our schedules. Objects follow the trajectories gravity dictates, not the desires of human observers. Thousands of bodies, from asteroids to planets, slip into conjunction every year. This is routine. To read intent into timing is to risk seeing patterns where none exist. And yet, this particular timing feels uncomfortably neat. Perihelion hidden. activity concealed, any possible change in trajectory or chemistry unfolding beyond our sight. For those inclined towards speculation, it looks less like chance and more like cover. If Atlas were an engineered craft, perihelion would be the perfect moment to perform a maneuver. A burst of acceleration, a controlled rotation, even a signal, all would occur while Earth's instruments are blind. When the comet emerges weeks later, we would only see the results, not the act itself. Astronomers will attempt workarounds. Solar observatories like SOHO and STEREO may capture indirect data, imaging dust plumes and plasma streams that extend beyond the sun's glare. These instruments lack the precision to decode chemistry, but they may reveal whether activity grows unusually intense. Mars orbiters might offer glimpses from their vantage point, though geometry will limit their reach. Ultimately, though, a curtain will fall across the most critical stage. The psychological weight of this blackout is profound. The universe is not supposed to tease us with mysteries, yet here we are, forced to wait while one of the strangest objects ever observed vanishes behind the sun. The questions multiply in the silence. Will it survive perihelion intact? Will its chemistry change dramatically? Will its orbit deviate from predictions? When Atlas re-emerges in December, astronomers will scramble to compare before and after data. Did it brighten, dim, fragment? Did its course shift? Only then will answers begin to emerge. Until that moment, we are left in suspense. Coincidence or cover? The truth hides in the glare of the sun. Spherex reveals a coma of carbon dioxide stretching 348,000 kilometers, larger than the distance from Earth to the Moon. What needs that much CO2? A comet's coma is its atmosphere, a vast cloud of gas and dust released as solar heat awakens frozen volatiles. Usually, water dominates, with other molecules playing secondary roles. But for Atlas, the star of the show is carbon dioxide. Its coma has swelled into an envelope so immense that Earth's entire orbiting companion could fit inside it. At this scale, the object is less a cometary nucleus than a planet-sized fountain, exhaling into the void. The numbers are staggering. A bubble of 348,000 kilometers exceeds even the widest earthly reference points. It is more than 27 Earth diameters across. For an object less than a few kilometers wide to produce such an envelope stretches our expectations. Where does the CO2 come from? How much ice must lie buried beneath its surface to sustain this output? And why does it dominate so completely over water vapor? Astronomers suggest the comet may have formed in an environment rich in frozen CO2, perhaps on the coldest fringes of its home system. If so, its chemical composition could be a clue to the diversity of planetary nurseries across the galaxy. A system farther out, or with different stellar radiation, could easily produce bodies dominated by carbon dioxide. Atlas may be a messenger, carrying evidence of worlds born in much colder realms. Yet the scale of the coma raises other questions. Sublimating gases usually disperse, thinning as they expand. For the CO2 bubble of Atlas to remain so prominent, production must be steady and powerful. Some scientists speculate that sunlight penetrates fissures on its surface, reaching deep reservoirs of frozen carbon dioxide. Each rotation may pump fresh jets into space, maintaining the enormous shroud. Others wonder whether unusual dust properties could trap and scatter CO2 more effectively, making it appear larger than expected. But speculation extends beyond natural processes. To the imaginative, a bubble this vast resembles not just a coma, but an exhaust. Could the release of CO2 be purposeful, a mechanism of control or concealment? To hide within a self-generated atmosphere would be a clever tactic, masking details of the nucleus from telescopic view. In this light, the coma becomes more than chemistry, it becomes camouflage. Science remains cautious, leaning on the principle that nature, given enough time and conditions, can produce wonders without intent. Even so, the sheer scale forces us to pause. No other comet studied has displayed such a dominant, moon-sized cloud of carbon dioxide. Whatever the explanation, Atlas is rewriting our understanding of what interstellar comets can be. The CO2 bubble is both a scientific gift and a mystery. It challenges us to think bigger, to accept that not all comets breathe alike. And as we picture this immense shroud drifting through the solar system, larger than the Earth-Moon distance, we are reminded that even small bodies can carry immense questions. Water signatures appear far from the Sun, earlier than expected. It should be frozen, yet it flows. In our solar system, comets typically begin releasing water vapor when they cross a critical boundary known as the frost line. At about 3 astronomical units from the Sun, roughly the distance of the asteroid belt, solar heat is finally strong enough to sublimate water ice into gas. Before that point, water remains locked inside, too cold to awaken. But Atlas defies this rule. Observations show water activity much farther out, at nearly twice that distance, where temperatures should be too low. Somehow, the comet is exhaling water early, far from the warmth that should free it. Astronomers are puzzled by this anomaly. One possibility is that Atlas carries supervolatile ices mixed into its crust. Carbon dioxide or carbon monoxide sublimation may act like an engine, blasting dust and buried water into space long before the Sun's heat could normally reach it. In this model, water does not sublimate directly. It is dragged outward by other volatiles erupting from within. Such a process has been suggested in solar system comets, but rarely so strongly. Another possibility involves unusual chemistry. If the comet's water contains dissolved salts or exotic compounds, it could behave differently under heat. These impurities might lower the sublimation temperature, allowing water to escape earlier than expected. This would suggest a birthplace very different from our own, where cometary materials were infused with elements unknown in our local reservoirs. But the early water raises more speculative ideas as well. If Atlas were engineered, then water emission at unusual distances could be interpreted as deliberate signaling, a visible anomaly designed to catch our attention. Jets of water at the wrong time become a kind of beacon, standing out against the backdrop of normal cometary behavior. While such ideas remain far outside mainstream science, the temptation to interpret anomalies through intent is hard to resist. Practical explanations remain likely. Cosmic rays bombarding the surface for millions of years could fracture the crust, leaving porous channels that allow water to escape at lower temperatures. Or the object may have experienced heating events in its distant past, altering the structure of its ices. If so, what we observe now could be the legacy of ancient processes, not evidence of anything deliberate. Still, the sight of water at the wrong distance forces us to rethink assumptions. We once believed comets were simple time capsules of frozen water and dust, but each interstellar visitor teaches us otherwise. Oumuamua revealed a body without a coma. Borisov reassured us with normal water activity. Atlas now disrupts that reassurance, showing us water where water should not be. The early flows remind us that the universe does not conform to our tidy categories. Nature is inventive, capable of surprises, and sometimes its surprises feel like whispers of design. Water, flowing from a frozen wanderer long before it should, is one such whisper. And whether the explanation is chemical, structural, or something stranger, the message is clear. We have much more to learn. Carbonyl sulfide, a rare molecule, emerges in its gas. A chemical fingerprint pointing to a birthplace far stranger than ours. In the study of comets, sulfur is a minor but intriguing player. On Earth, sulfur is tied to volcanoes, deep-sea vents, and the chemistry of life. In space, it is present in trace amounts, woven into ices and dust, usually locked within molecules like hydrogen sulfide or sulfur dioxide. Carbonyl sulfide, COS, is much less common. Detecting it in Atlas is not only unexpected, it is provocative. Why? Because carbonyl sulfide requires very specific conditions to exist in significant amounts. Laboratory experiments show that it forms on the surfaces of cold dust grains. where carbon monoxide and sulfur atoms can combine under ultraviolet radiation. In our solar system, such chemistry occurs in the frigid outer regions of molecular clouds, long before stars and planets condense. For Atlas to carry COS so prominently means it may have been born in an environment rich in sulfur and bathed in cosmic radiation, a place more extreme than our local nursery. Some scientists see COS as more than a geological clue. On Earth, carbonyl sulfide has been studied as a potential biosignature. It can be released by biological activity, particularly in microbial ecosystems. This does not mean Atlas is alive or that life played any role in shaping it, but the association sparks curiosity. Could the molecule be telling us that conditions for life were present in its birthplace? Could sulfur chemistry be part of a universal recipe for habitability? More conservative voices point out that sulfur compounds are tricky. They can survive interstellar journeys precisely because they are resilient, forming stable ices that cling to dust for millions of years. What we see in Atlas may simply be a chemical fossil, preserved through eons, not evidence of anything active or unusual. Still, even as a fossil, it is revealing. It tells us that planetary systems elsewhere must produce comets with very different chemistries, shaped by local conditions we are only beginning to imagine. The sulfur clue also raises practical questions. Why is COS detectable when other sulfur molecules are faint? Does this mean Atlas's surface has been selectively processed, perhaps by cosmic rays stripping away weaker compounds? Or does it mean the interior is uniquely rich in COS, a reservoir now venting as the comet heats? Either way, its prominence marks Atlas as chemically exotic, far removed from the water-dominated comets of our skies. And then there is the speculative edge. To the imaginative, COS is more than an anomaly. It is a signal. If one were to design a cometary disguise, loading it with unusual chemistry would make it conspicuous, ensuring it would be noticed. The thought is unsettling, yet impossible to fully dismiss in the atmosphere of mounting anomalies. In truth, the sulfur clue deepens the mystery rather than solving it. Whether born of cold interstellar chemistry, preserved as a fossil from a distant nursery, or hinting at stranger processes, carbonyl sulfide in Atlas reminds us of the diversity of worlds, and as its gases stream into space, they whisper of a birthplace stranger, colder, and perhaps richer than our own. Some scientists whisper, is Atlas a planet seed, carrying the recipe for worlds, a gardener's tool drifting between stars? The idea may sound poetic, but it has roots in real science. Planetary systems are not built all at once, they are assembled grain by grain, rock by rock, ice by ice. In the early days of any star system, small bodies like comets and asteroids are the bricks from which larger worlds grow. They bring ices, metals, and carbon compounds together, colliding, merging, and accreting into planets. In this sense, a comet is not just debris, it is potential. And an interstellar comet like Atlas could carry that potential across the galaxy. Imagine the long history of such objects. Born in distant nurseries, ejected by the gravitational chaos of young giant planets, they wander endlessly between the stars. Each one is a capsule of raw ingredients: water, carbon dioxide, organics, sulfur compounds, even trace metals like nickel. If they collide with other systems, they could act as sparks, sprinkling alien nurseries with the seeds of planets, the building blocks of habitability. In this framework, Atlas is not just a curiosity, but part of a vast cosmic distribution system. The concept has a name, panspermia. Usually, the term refers to the spread of life, the idea that microbes might hitchhike between worlds, but on a broader scale, it applies to chemistry as well. Comets could spread not living cells, but the recipes that allow life to emerge once planets form. With its immense carbon dioxide bubble, its water signatures, and its strange sulfur fingerprints, Atlas may carry such a recipe. Some researchers even suggest comets like Atlas may be essential to life spread. Without them, many worlds might remain barren, lacking key volatiles. Earth itself may have been seeded by icy bodies long ago, delivering water to a dry young planet? If so, then comets are gardeners of the galaxy, messengers carrying the materials of habitability wherever chance delivers them. In this light, Atlas is not alien, it is family. And yet, its strangeness makes the story more complex. Could Atlas represent a different flavor of planetary seed, born in colder realms with chemistry alien to ours? If such comets fall into young systems, the planets they help build may look nothing like Earth. Atmospheres may form under the weight of carbon dioxide, or sulfur compounds may play a role unknown to us. In that sense, Atlas carries not just ingredients but possibilities, new recipes for worlds beyond our imagination. Speculation stretches further. Some wonder, could such seeding be deliberate? If an advanced civilization wished to spread life or terraform distant systems, scattering engineered comets would be a logical method. Comets are durable, capable of surviving eons of travel, and their impacts can transform planets. Is Atlas simply natural, or could it be a gardener's tool, crafted with purpose? For now, science leans toward chance. But the vision persists. Atlas, as a wandering seed, a gardener of the cosmos. Whether by accident or by design, it carries the recipe for worlds, drifting silently, waiting for fertile ground. If not a rock, then could it be alive? Protected microbes asleep in its core, waiting for warmth to awaken them? The notion belongs to the realm of panspermia, the ancient idea that life may not be confined to single planets but may instead drift between stars, carried by comets, asteroids, or even interstellar dust. If microbes can survive deep freezing, radiation, and the vacuum of space, then an object like Atlas could be more than a lump of frozen chemistry. It could be a capsule, a vault, a seed. On Earth, extremophiles have already taught us that life is tougher than we once believed. Microbes thrive in boiling hydrothermal vents, endure the crushing pressures of the deep ocean, and even survive exposure to the vacuum of space for limited periods. Deinococcus radiodurans, sometimes called Conan the bacterium, can withstand intense radiation doses. Tardigrades, microscopic animals, have been revived after years in a frozen state. These examples prove that biology can adapt to conditions far harsher than the surface of our comfortable planet. If life arose elsewhere, perhaps it too could find ways to endure deep time, sleeping within icy fragments. In this framework, Atlas becomes more than chemistry. Its unusual carbon dioxide dominance, its sulfur fingerprints, its early release of water, all could be interpreted as signs of a body carrying complex materials, perhaps even dormant biology. If frozen microbes are encased in its nucleus, perihelion could act as a trigger. Heat from the sun might melt protective ices, reawakening cells that have lain dormant for millions of years. The comet's coma would then not just be vaporized gas, but the breath of alien biology. Scientists tread carefully here. There is no evidence of life in Atlas, only the possibility of conditions that could support it. But possibilities matter. In 1984, meteorite ALH 8400, one from Mars, sparked debate after microscopic structures were interpreted as fossil bacteria. That claim remains controversial, but it opened the door to new questions. If Mars could potentially preserve traces of life, then why not an interstellar comet? Skeptics point out the difficulties. Radiation in interstellar space is intense. Over millions of years, cosmic rays would sterilize surface layers. To protect microbes, Atlas would need to bury them deep within, under meters of shielding ice. Even then, energy sources would be scarce. Could life survive without nutrients for so long? Could it truly endure millions of years in a frozen stasis, only to reawaken when sunlight returned? These are not small questions, and biology has not yet answered them. Yet hope persists because the stakes are profound. If Atlas carries life, or even the building blocks of life, it would mean biology is not unique to Earth. It would suggest the galaxy is alive with seeds, scattered widely, waiting for fertile ground. Life would not be an accident, but a cosmic inevitability. So, Is Atlas alive? Probably not. But the hypothesis is worth asking. Because in asking, we remember that life clings to possibilities. And perhaps, somewhere deep inside that wandering fragment, possibility is exactly what lies asleep, waiting. If not alive, then could it be a machine? A probe cloaked in cometary disguise, studying us while we argue over its nature. This idea is not new. When Oumuamua streaked through the solar system in 2017, Harvard astronomer Avi Loeb proposed that it might be artificial, a thin, light sail-like craft propelled by starlight. The suggestion was controversial, sparking fierce debate among scientists. Most dismissed it as unlikely, preferring natural explanations. But the seed was planted. If interstellar civilizations exist, how might their probes appear to us? Would they reveal themselves openly, or would they hide in plain sight, disguised as ordinary rocks and comets? Atlas invites this question anew. Its behavior is comet-like, yet filled with anomalies. The dominance of carbon dioxide over water, the strange nickel without iron signature, the forward-facing glow, the eerie rhythm of its light curve, each one is explainable in isolation. Yet together, they tempt us towards speculation. Could these be the hallmarks of design, features meant to mimic nature while concealing technology beneath? Imagine, for a moment, what a disguised probe would need. First, a protective shell, ice and dust, shielding instruments from radiation and disguising its core. Second, a trajectory, a path that brings it near planets, the Sun and Jupiter, each an opportunity to gather data. Third, a power source, perhaps sunlight itself or nuclear fuel buried deep inside. And finally, patience. The kind of patience only machines possess, drifting for millions of years until one day they intersect a system like ours. Science fiction has long imagined such possibilities. Arthur C. Clarke's Rendezvous with Rama described a cylindrical alien craft mistaken for an asteroid. The idea resonates because it plays on a truth. Our instruments are limited, and a clever probe could easily appear natural until studied up close. In the case of Atlas, our distance ensures that no spacecraft can intercept it in time. If it were artificial, its disguise would remain intact, leaving us with nothing but questions. Skeptics are quick to remind us that extraordinary claims demand extraordinary evidence. No radio signals, no structured emissions, no repeating patterns that would suggest machinery. What we see could be entirely natural, strange chemistry, exotic dust, and geometry shaped by billions of years in interstellar space. To leap to machine too quickly risks turning science into speculation. Yet curiosity lingers, because the hypothesis itself is worth considering. If civilizations exist elsewhere, probes are more likely than ships. Machines are tireless, resilient, and capable of journeys far longer than the lifespan of any species. If one wished to explore the galaxy quietly, a cometary disguise would be clever indeed. Natural debris is common. Nobody would notice until anomalies arose, and by then, it would already be too late to get close. For now, Atlas remains unproven, its core unseen. But the technology hypothesis remains on the table, not as a claim, but as a reminder. The universe is vast, and we should remain open to the possibility that some visitors may not simply be rocks, but relics of intelligence, hiding in plain sight. What if silence is survival? What if hiding behind the sun is the strategy of a visitor that does not wish to be seen? This idea emerges from the dark forest hypothesis in cosmology and the search for extraterrestrial intelligence. The metaphor is haunting. Imagine the universe as a vast, dark forest. Each civilization is a hunter, quietly moving through the trees. To announce oneself with noise or light is to risk being discovered by something stronger, something less benevolent. In such a forest, survival depends on silence. Do not shout. Do not signal. Do not reveal your position. Applied to Atlas, the concept takes on a chilling resonance. Its closest pass to the Sun, perihelion, will occur during solar conjunction, when Earth cannot observe. For weeks, it will be invisible, hidden in the Sun's glare. Coincidence, perhaps. But what if this invisibility is not chance but strategy? If Atlas were more than a natural body, perihelion would be the perfect time to maneuver, to change course, or even to transmit, shielded from our detection. Behind the curtain of the Sun, it could act without witnesses. From one perspective, this is pure speculation. Orbital mechanics explain conjunction easily. Countless planets and comets vanish into solar glare every year, with no intent at all. Yet the timing nags at the imagination. Just when we most want to watch, the object slips away. If one were inclined to see strategy, the dark forest provides a framework. Silence, concealment, and survival as universal laws. Astronomers, of course, prefer natural explanations. Dust jets, gravitational perturbations, and sunlight pressure account for most deviations. The absence of radio signals from Atlas strengthens the case for nature over intent. Yet, even the silence can feel suspicious when filtered through the dark forest lens. What if civilizations everywhere remain mute because the loud ones never survive? There is also a psychological weight to the idea. Humanity longs for connection, for evidence that we are not alone. But we also carry fear that others may not greet us with curiosity, but with caution or hostility. The dark forest theory reflects that fear, reminding us that survival may demand invisibility. In this sense, Atlas becomes a mirror, reflecting our own anxieties as much as our observations. When it emerges from conjunction in December 2025, astronomers will search for differences. Did its orbit shift? Did its brightness change in ways unexplained by sunlight? If it emerges exactly as predicted, then the simplest explanation, chance, will prevail. But if something has altered, even subtly, then whispers of the dark forest will grow louder. For now, Atlas remains an enigma. It may be nothing more than frozen rock and gas, behaving in ways we do not yet understand, or it may embody the caution of a cosmos where survival depends on silence. In the dark forest of the universe, perhaps even visitors know, to be seen is to risk everything. Light scattering from its dust doesn't match anything we know. Its optical signature is not like other comets. What kind of grains shine this way? When light reflects off dust, it doesn't simply bounce, it changes. The orientation of the light waves becomes altered, a property scientists call polarization. By studying polarization patterns, astronomers can infer the size, shape, and structure of dust grains surrounding comets. For decades, this technique has revealed remarkable consistency. Comets in our solar system tend to scatter light in familiar ways, their dust following patterns born from silicates, carbon, and ice. But Atlas is different. Its polarization curves refuse to conform. Observations show angles of polarization that do not match standard models. Instead of the expected gradual shift as sunlight scatters through a coma of mixed grains, Atlas displays sharp deviations. Larger, more porous grains could explain some of the effect. Exotic compositions, perhaps rich in carbon dioxide ice or sulfur compounds, could explain others. But the precise match eludes us. Its dust does not behave like cometary dust we know. The mystery deepens because polarization is not just an academic detail, it is a fingerprint. It carries the mark of the environment in which the grains were formed. Dust that polarizes in one way may have condensed in dense molecular clouds. Dust that polarizes differently may have formed closer to a star, altered by heat and radiation. By this logic, Atlas's strange polarization suggests a birthplace very unlike our solar system's nursery. Some astronomers propose that the grains are unusually fluffy, aggregates of fine particles loosely bound, like cosmic snowflakes. Others suggest the presence of metallic elements woven into the dust, altering the way light scatters. Both explanations remain speculative, because laboratory simulations cannot yet reproduce the precise polarization patterns observed. Atlas resists replication, remaining stubbornly unique. Then there are the more speculative voices. To them, polarization anomalies evoke something engineered. Polarized light is, after all, a tool we use in our own technology, from sunglasses to communication systems. If Atlas's grains are not natural, but manufactured, could their scattering serve a purpose? Could the optical oddities be more than byproducts? Could they be signals? This leap, while captivating, remains firmly outside mainstream science. Yet the idea persists, fueled by the unease that comes when data does not fit known categories. Even within conservative circles, the anomaly matters. The more we study polarization, the clearer it becomes that Atlas is not just chemically unusual but structurally distinct. Its grains are telling us that planetary systems across the galaxy are capable of producing dust unlike anything we have seen. Whether natural or otherwise, the lesson is profound. The universe is more diverse than our expectations allow. The polarization mysteries of Atlas are not solved yet, but they remind us that even in something as delicate as scattered light, strangeness can emerge. And as its dust continues to shine in unfamiliar ways, the question lingers. What kind of grains glow like this? And what story do they carry across the stars? Some say it could be as small as 400 meters. Others, over 5 kilometers. The truth changes everything: mass, gravity, even survival. Measuring the size of an interstellar object is deceptively difficult. Unlike planets or moons, which can be directly imaged as disks, comets appear as fuzzy points of light surrounded by glowing comae. The nucleus itself is hidden, wrapped in layers of dust and gas. To estimate its size, astronomers must rely on indirect methods: brightness, thermal emission, and models of reflectivity. With Atlas, those estimates diverge sharply. At the low end, some observations suggest a nucleus only a few hundred meters across, smaller than a city, barely larger than a skyscraper. At this scale, Atlas would be fragile, a loosely bound rubble pile venting gas far more vigorously than expected for its size. Such a small body would raise questions about survival. Could it endure perihelion, or would it fragment under solar heat and tidal stress? If it shatters, Earth may never know what secrets its intact form concealed. At the higher estimates, Atlas could stretch several kilometers across. A body this large would carry immense mass and inertia, shrugging off the sun's heat with ease. It would also mean its carbon dioxide coma is even more extraordinary, because such a giant nucleus should be dominated by water, not CO2. The larger the comet, the stranger its chemistry becomes. And with greater mass comes greater influence. Its gravitational field, though tiny compared to planets, would shape its coma in measurable ways. Detecting that influence could finally pin down its size. The uncertainty also extends to its implications. If Atlas is small, then its dramatic gas output might be explained by surface processes, with volatile rich layers erupting as they are exposed. If it is large, then those same outbursts suggest a deep global reservoir of carbon dioxide, an entire worldlet, unlike anything seen in our solar system. Size determines origin story. A shard versus a miniature planet. The debate carries echoes of Oumuamua. That object's extreme shape and brightness made its size difficult to constrain, with estimates varying wildly depending on assumptions about reflectivity. Some proposed it was a thin, flat object, no more than a few dozen meters thick, catching sunlight like a sail. Others saw it as a darker, bulkier shard. Atlas repeats this uncertainty, though with more data available, thanks to its coma. Yet the answers remain elusive, shifting with every new observation. Speculation stretches further. If Atlas is closer to the smaller end of the spectrum, might it be hollow? Could the apparent gas production be exaggerated by cavities within, storing and releasing CO2 in bursts? Conversely, if it is larger, could we be looking at a survivor of planetary formation? A fragment of a dwarf planet, ejected into the interstellar void billions of years ago? Each scenario paints a different picture of its role in cosmic history. Ultimately, the size question is not just academic. It determines whether Atlas is a fragile shard on the edge of disintegration or a massive, enduring traveler built to last eons. Somewhere between skyscraper and mountain lies the truth, and in that truth may rest the key to its survival, and ours. If, after solar conjunction, its orbit no longer matches predictions, we'll know something is pushing it. Something more than sunlight and ice. In celestial mechanics, orbits are precise. Once astronomers calculate the position, velocity, and gravitational influences on an object, they can forecast its path with extraordinary accuracy. For most comets, minor deviations do occur, but they can be explained. Jets of gas venting from a rotating nucleus act like tiny thrusters, nudging the body slightly off course. These non-gravitational accelerations are well understood. They're expected, even routine. But with interstellar visitors like Atlas, the stakes are higher. Any drift beyond predictions could hint at something stranger. The precedent is Oumuamua. In 2017, its trajectory shifted subtly in ways gravity alone could not explain. No visible coma, no obvious jets, yet its orbit changed. Some proposed hydrogen ice sublimating invisibly. Others suggested exotic dust or even a thin, sail-like structure pushed by sunlight. The lack of a clear explanation gave birth to the first serious whispers of alien technology. With Atlas, astronomers are prepared. Its orbit has been mapped in detail, projected forward past Mars, perihelion, and its close encounter with Jupiter in March 2026. If the object follows predictions, it will reinforce the cometary explanation. Gas jets, outbursts, and sunlight pressure in familiar balance. But if it drifts, if its path after conjunction fails to align with models, then questions will sharpen. What is propelling it? There are natural options. Sublimating carbon dioxide can exert stronger forces than water, especially given Atlas's immense CO2 coma. If jets erupt asymmetrically, they could produce significant thrust, altering the orbit more than typical comets. Likewise, fragmentation could shift its momentum, changing its path subtly. These are plausible, and most astronomers expect them. But speculation lingers, because drift is the language of control. A probe with propulsion would leave exactly this kind of fingerprint. A course not quite matching predictions, a subtle correction disguised as cometary behavior. If Atlas were maneuvering, conjunction would be the perfect time. Shielded by the sun's glare, any change would go unseen until it emerges weeks later. By then, we would only see the aftermath, an orbit that no longer fits. The implications of such a deviation would be profound. If Atlas moves in ways natural outgassing cannot explain, then either our understanding of comet physics is incomplete or something else is at work. Scientists will look for patterns. Does the drift align with sunlight pressure? Does it repeat predictably? Or does it point in directions no natural jet should? The answers could separate dust physics from design. When Atlas emerges from conjunction, astronomers will track it obsessively, measuring its position against predictions to the precision of kilometers across millions of miles. Even the smallest anomaly will matter. It will either confirm the cometary model or reopen the debate that began with Oumuamua. For now, the object glides forward, its orbit still matching expectations. But the real test is yet to come. If Atlas drifts, the mystery deepens. If it holds steady, the universe remains strange, but perhaps not deliberate. Either way, its trajectory is not just motion through space. It is a message, written in gravity, and perhaps in something more. No narrowband radio signals, no obvious artificial light. But absence of evidence is not evidence of absence. What should SETI even look for? For decades, the search for extraterrestrial intelligence, SETI, has tuned its antennas to the sky, listening for signals that might betray the presence of other civilizations. The classic expectation has been narrowband radio transmissions, something deliberate and distinct from the broad, noisy chatter of natural sources. And yet, despite scanning millions of stars, no confirmed signal has ever been found. Now, with Atlas passing through our solar system, SETI faces a question. How do you search for intent in an object that looks, at first glance, like a comet? Radio telescopes have already swept across Atlas's position. They have found nothing unusual. No pulsed beacons, no narrowband emissions, no structured communication. Optical telescopes too have searched for artificial light. Flashes, lasers, repeating pulses, and again, nothing has appeared. The data so far is silent. But silence, SETI researchers remind us, does not mean emptiness. What if the signals are subtle? What if we are listening in the wrong way? One dilemma is assumption. Humanity imagines aliens will communicate as we do, using technologies familiar to us. Radio, lasers, microwaves. But an advanced civilization may use physics we do not yet master. Quantum communication, neutrinos, or methods entirely outside our grasp. If so, our antennas are as blind as ears pressed against a silent wall. Even if Atlas were transmitting, we might not know how to hear it. Another dilemma is intent. Why would a probe or a disguised visitor signal us at all? If the dark forest hypothesis is true, survival favors silence. A probe might observe but never announce itself, collecting data quietly, blending in with the background of natural objects. If so, SETI's search for overt signals may be misguided. We may need to look not for communication, but for anomalies, behaviors, or signatures that suggest design rather than accident. In this light, the work of SETI expands beyond listening. Polarization anomalies, strange chemistry, unusual trajectories, all could serve as technosignatures, hints of technology without deliberate messages. Atlas's forward glow, its nickel without iron, its massive CO2 coma, each could, in theory, belong to this broader category. The challenge is that nature, too, produces surprises. Distinguishing the artificial from the exotic natural is the hardest puzzle of all. SETI's dilemma, then, is not just technical but philosophical. Do we expect intelligence to reach out openly, or do we expect it to remain hidden? Do we focus on listening, or do we broaden our search to include every kind of anomaly? And perhaps most importantly, if we did find evidence, would we even recognize it? As Atlas drifts closer to the sun, the silence continues. No beacons, no lights, no clear signal. But absence of evidence is not evidence of absence. The universe has taught us time and again that the unexpected often masquerades as the ordinary, and perhaps the real signal is not in radio waves at all, but in the very strangeness of the visitor itself. A dart thrown from a mile away landing at your feet feels deliberate. Is Atlas the same? The universe is vast, unimaginably so. Trillions of stars, billions of galaxies, and countless planets fill the dark. Against this backdrop, the odds of an interstellar object passing through our solar system at all are slim. To then find that it threads a path near Mars, passes behind the Sun at perihelion, and brushes past Jupiter in a matter of months seems almost uncanny. Each encounter could, in principle, be coincidence, yet together they invite a question. Are we simply watching the dice of the cosmos fall in improbable ways? Or is there a pattern hiding in the randomness? Astronomers lean toward probability. Space is full of debris ejected from young planetary systems in gravitational chaos. Over time, these wanderers drift between the stars. Given enough time, some of them must intersect with ours. Statistically, it is not impossible that one such body might just happen to align with Mars, the Sun, and Jupiter in sequence. The dart, though unlikely, can land at our feet by chance alone. But chance does not feel satisfying. Human minds are wired to find patterns, to connect dots, to search for meaning. When Atlas follows a path that allows multiple opportunities for observation and potential concealment, it feels deliberate. Mars, where orbiters can watch, the Sun, where Earth goes blind, Jupiter, whose gravity dominates the system. If this were a reconnaissance mission, the trajectory could hardly be more effective. The analogy of a dart sharpens into suspicion. How likely is it that blind chance would write choreography this neat? Science, however, warns against overinterpreting. The sample size is painfully small. We have seen only 3 interstellar objects, Oumuamua, Borisov, and Atlas. With so few data points, we cannot yet judge what is normal. Perhaps many interstellar comets naturally fall into alignments that seem meaningful. Or perhaps most do not, and Atlas is an outlier. Until we see dozens or hundreds, our sense of probability remains little more than intuition. Yet coincidences matter. They provoke us to look closer, to test assumptions, to design better models. Even if Atlas is a purely natural visitor, its path highlights the limits of our knowledge. Perhaps planetary alignments are more influential than we realized, sculpting interstellar trajectories in subtle ways. Or perhaps our own observational bias, what we can and cannot see, skews the story, making its encounters feel more extraordinary than they are. And then there is the philosophical angle. Coincidences can be clues, depending on how we interpret them. To dismiss them entirely risks missing signals hidden in plain sight. To embrace them too eagerly risks chasing illusions. The truth may lie somewhere in between, chance that feels like design, and design that hides within chance. So, is Atlas just a dart falling by accident into our solar system's heart? Or is it something more, a clue, a message, a pattern we are only beginning to perceive? For now, we cannot know. But the very act of asking reminds us how little separates coincidence from meaning in the vast dark of the cosmos. The nickel anomaly, the forward glow, the CO2 dominance, each could be natural, but together, do they cross the line into technology? When faced with unusual data, science begins with the simplest explanation. For Atlas, each mystery has a potential natural cause. The nickel without iron may result from excitation conditions in spectroscopy, where nickel atoms radiate more efficiently than iron under specific energies. The forward glow could be a matter of dust scattering, grains of just the right size throwing sunlight forward in unusual patterns. The massive carbon dioxide coma might reflect an origin in a particularly frigid nursery, where CO2 froze in abundance. None of these explanations is impossible. Each one has precedent, if only in fragments. But the challenge lies not in isolation, but in accumulation. When anomalies stack, they begin to weigh heavier on the imagination. A forward glow alone would intrigue but not astonish. Nickel without iron would puzzle but not provoke. Carbon dioxide dominance could be shrugged off as unusual chemistry. But all three, together, begin to feel like something more, like a pattern that resists easy dismissal. It is here that speculation stirs. What if these traits are not quirks of geology, but signatures of intent? A probe disguised as a comet might release carbon dioxide deliberately, both as propellant and camouflage. Nickel-rich materials could be part of its engineered core, selected for structural strength or radiation shielding. The forward glow might not be scattering at all, but emission, energy released by mechanisms we cannot yet detect. Seen this way, Atlas ceases to be a wayward rock and becomes instead a machine, its disguise imperfect under the scrutiny of our instruments. Skeptics counter with caution. Nature is inventive. Rare alignments of chemistry, geometry, and physics can mimic design without ever requiring it. And history warns us that anomalies often collapse under closer study. The canals of Mars, once thought artificial, turned out to be optical illusions. Pulsars, first nicknamed LGM for Little Green Men, revealed themselves as neutron stars. In time, Atlas's strangeness may find its mundane explanations. Yet the question is worth asking, because it sharpens our inquiry. To treat anomalies as potential technology does not mean declaring them so. It means testing them more rigorously, designing observations that can separate natural from artificial. Is the nickel line truly devoid of iron, or is it a matter of sensitivity? Does the forward glow match models of exotic dust scattering, or does it deviate in ways we cannot yet explain? These are testable questions, and asking them with open minds honors both science and imagination. At its heart, the debate is philosophical. How much strangeness do we allow before we entertain extraordinary possibilities? When does chemistry cross the threshold into suspicion? And if technology hides within the guise of nature, how would we recognize it? Atlas forces us to confront these questions, not because it has proven itself artificial, but because it refuses to fit neatly into the box of the familiar. Alien chemistry? Alien craft? For now, the line remains blurred, and in that blur, our curiosity lingers, suspended between dust and design, waiting for the universe to reveal its hand. Science thrives on the unusual. But when anomalies pile up, at what point do we ask the forbidden question? Are we alone? Anomalies are the fuel of discovery. They are the cracks in the familiar, the places where nature refuses to conform to our expectations. Without them, progress would stall. The orbit of Mercury, for instance, once stubbornly refused to match Newton's laws until Einstein revealed the deeper framework of general relativity. The faint glow of the cosmic microwave background was an unexpected hum of static, one that became the smoking gun for the Big Bang. Time and again, it is the outliers, not the norms, that expand our understanding of the universe. Atlas is such an outlier. Its nickel without iron, its forward-facing glow, its immense carbon dioxide bubble and water activity at impossible distances. Each observation could be explained away with patience, with models stretched and adjusted. But together, they form a chorus of strangeness. The temptation is to dismiss them as errors, quirks of measurement or interpretation. Yet history whispers a warning. Anomalies should not be ignored. They are the places where truth hides. The philosophy of anomalies is a balancing act between skepticism and imagination. Too much skepticism, and we risk overlooking discoveries, treating the unusual as noise. Too much imagination, and we risk falling into fantasy, seeing patterns where none exist. The discipline of science lies in the middle path, to doubt, but also to wonder, to treat anomalies not as inconveniences, but as invitations. And yet, one question looms larger than all others. Are anomalies merely windows into deeper physics? Or could they be hints of something more? When we ask, are we alone? We tread into territory science has long avoided. For centuries, the idea of alien intelligence has been framed as philosophy, speculation, or fiction. But interstellar visitors like Atlas force the question back onto the table. If nature is capable of producing such strangeness, then perhaps it is also capable of producing intelligence. And if intelligence can arise, why not technology? Why not probes disguised as comets, drifting silently through the dark? The forbidden question is not dangerous because it is foolish. It is dangerous because it is profound. To ask it is to admit that we do not know, that our models may be incomplete, that our universe may be populated in ways we have barely begun to imagine. To ask it is also to risk ridicule, for science still values restraint, but restraint must not become blindness. Atlas, like Oumuamua before it, reminds us that the cosmos does not conform neatly to our categories. Some anomalies will collapse under better data, explained by dust physics, exotic chemistry, or the quirks of observation. But some may not. And when they do not, we will be forced to ask again, are we alone? In this sense, anomalies are not merely scientific puzzles, they are philosophical tests. They ask not only what we know, but what we are willing to imagine. And they remind us that the universe may be stranger and richer than our most careful skepticism allows. The less the agencies say, the louder speculation becomes. Silence is not empty. It is filled by imagination. Since the discovery of Atlas, the official voices have remained muted. NASA and ESA have published quiet technical notes, but little more. No sweeping press conferences, no bold interpretations, just data, stripped of narrative. On the surface, this caution makes sense. Astronomers learned hard lessons from Oumuamua when headlines leapt to alien spacecraft before the science was settled. This time, agencies appear determined to understate rather than overstate. But public silence is not the same as public reassurance. In the absence of explanations, curiosity takes its own course. Online forums erupt with speculation. Is the forward glow a beacon? Is the CO2 dominance camouflage? Why does the object skim past Mars, vanish behind the Sun, and then approach Jupiter in such a precise sequence? Without official commentary, every anomaly becomes fertile ground for theory. And while some theories remain grounded in science, others drift toward conspiracy. Governments, after all, carry the weight of secrecy in other domains. Military programs operate behind closed doors, intelligence reports stay classified, and sensitive discoveries are often released only after long delays. Against this backdrop, the restraint around Atlas feels less like caution and more like concealment. If nothing unusual is happening, why not say so plainly? Why the hesitance to engage the public with wonder? History offers examples of similar dynamics. The early years of the space age were full of withheld information, from classified rocket failures to military satellite launches cloaked in vague terminology. Even now, objects in orbit are routinely tracked by defense networks, but not shared openly with the public. When an interstellar body with strange properties arrives, it is easy to assume the same culture of secrecy applies. Of course, there are practical reasons for restraint. Speculation about alien probes can inflame fears, distract from serious science, and distort public perception. Officials may choose silence simply to prevent sensationalism. Better, perhaps, to let anomalies be worked out in journals than risk fueling panic or ridicule. But intention and perception diverge. What feels like prudence to agencies feels like mystery to the public. Silence becomes noise. This interplay between secrecy and speculation highlights a deeper truth. People crave narrative. We want meaning, not just numbers. A coma 348,000 kilometers wide is a fact, but it begs for a story. Why so large? Why carbon dioxide? Why now? When governments decline to provide one, the human imagination supplies its own. And imagination rarely errs on the side of the ordinary. Thus, the official quiet around Atlas becomes part of the mystery itself. Silence becomes suspicious. Each withheld detail feels deliberate. The less is said, the more is believed. And so Atlas, whatever its true nature, transforms from a cometary visitor into a canvas for our fears, our hopes, and our speculations. In the end, perhaps agencies underestimate the human appetite for wonder. Silence is not neutrality, it is narrative. And in the case of Atlas, it may be the loudest narrative of all. In December 2025, Atlas will re-emerge. What will we see then? A comet unchanged or something transformed? For weeks after perihelion, the object will vanish into the glare of the sun. No Earth-based telescope will track it. Even our most advanced observatories, from Hubble to the James Webb Space Telescope, will be blinded by solar proximity. It is a blackout, a curtain drawn at the most critical moment. And then, like a performer stepping back into the light, Atlas will reappear in the evening sky. Comets often change during their closest approach to the sun. Some survive, their cores intact, exhaling more vigorously than before. Others fracture into pieces, overwhelmed by heat and tidal stress. The difference depends on size, structure, and composition. If Atlas is small, perhaps only a few hundred meters wide, perihelion may prove fatal. It could disintegrate, leaving only a fading cloud of dust behind. If it is large, kilometers across, it may endure, carrying its mysteries forward to the rendezvous with Jupiter. But survival is not the only question. Change is. Will its chemistry shift? Will new gases appear, revealing layers once hidden? If water activity strengthens dramatically, it may confirm theories that deeper ices were waiting to awaken. If its CO2 dominance persists, then the mystery deepens. Why is this comet so different from our own? Astronomers will compare pre- and post-perihelion spectra closely, searching for evolution in its fingerprint. Its orbit will also come under scrutiny. Predictions place it on a hyperbolic path, bending around the Sun before sailing outward again. If it follows that curve precisely, all is well. If deviations appear, non-gravitational drifts beyond what jets of gas can explain, then speculation will ignite anew. Conjunction provides the perfect cloak for any maneuver. Only when Atlas re-emerges will we know whether it stayed true to its predicted path. The brightness curve will be another clue. If the comet dims more than expected, fragmentation may have occurred. If it brightens, perhaps the heat awakened buried volatiles. And if it pulses in rhythm, continuing its strange breathing light curve, then questions about its rotation and its nature will remain. For astronomers, December 2025 is not just a checkpoint, it is a reveal. A chance to see whether the universe has offered us another puzzle piece or removed one from the board entirely. Will Atlas emerge as a comet that simply stretched our imagination, or as something that forces us to redraw the boundaries of the possible? And for the public, the re-emergence will be symbolic. The dark curtain of conjunction holds all our questions in suspense. When it rises, we will finally glimpse answers or deeper mysteries. Perhaps Atlas will appear unchanged, a wanderer following natural laws, or perhaps it will return transformed, carrying secrets written in its light and orbit. Whatever happens, December will mark a turning point. A moment when speculation meets reality. A glimpse beyond the Sun into either reassurance or revelation. On December 19th, 2025, 3I Atlas is expected to make its closest pass to Earth. Even then, it will not come near in human terms. It will remain tens of millions of kilometers away, far more distant than the Moon and no threat to Earth. Yet this moment carries weight, because it will give astronomers their sharpest view of the object before it drifts back into the dark between stars. For scientists, closest approach is a chance for clarity. Instruments on Earth and in orbit will measure its brightness, track its spectrum, and test whether its trajectory still aligns with predictions. If its orbit holds steady, much of the mystery may quiet. But if its path shifts unexpectedly, if it drifts in ways that cannot be explained by carbon dioxide jets alone, then speculation will sharpen. Speculative theories already circulate, fueled by its anomalies. Some imagine Atlas fragmenting during its solar passage, breaking into smaller pieces that leave a trail of dust. If so, Earth's skies might one day see faint meteor activity as fragments scatter harmlessly across space. Others suggest its chemistry could trigger a sudden brightness surge, transforming it into a comet visible even without telescopes, a fleeting spectacle. The more adventurous ideas lean further into the unknown. What if Atlas is not entirely natural? Its path, near Mars, behind the Sun, past Jupiter, and then by Earth, feels almost like reconnaissance. In that light, closest approach could be interpreted as observation, a chance for a hidden probe to take its best look at our planet. Still others imagine it as a carrier of life, scattering organic molecules into the solar system as part of panspermia, seeding new beginnings far from its home. And then there are the more symbolic views, that Atlas is a harbinger, not of disaster, but of perspective, a reminder that we live in a universe of travelers, and that even in our small corner of the galaxy, we are not isolated from the grand currents of interstellar space. It is important to say, though, that these ideas remain firmly speculative. Astronomers stress that Atlas poses no danger to Earth, its closest approach will be distant, and its mysteries are scientific puzzles, not threats. The value lies in the questions it raises, not in fears of collision. So what will we see on December 19th, 2025? Likely a faint point of light, carefully studied by telescopes, offering clues to its strange behavior. Perhaps no more than that, yet even this modest glimpse is extraordinary. For a moment, we will be watching an interstellar traveler as it sails closest to our home world, before it drifts away into the deep dark once more. Closest approach, then, is not a moment of danger, it is a moment of wonder, a fleeting reminder that we are part of a larger story, written not only in planets and stars but in travelers like Atlas, who carry questions across the void. If natural, then 3i Atlas still rewrites our models of planetary chemistry, cometary diversity, and interstellar origins. A gift of knowledge. It is easy, when confronted with anomalies, to leap toward the extraordinary. Alien probes, hidden technology, even living seeds drifting between stars, such ideas capture the imagination. But the quieter truth may be just as profound. Even if Atlas is nothing more than a comet, its very strangeness changes what we know about the universe. It stretches the boundaries of what we thought possible, forcing us to rewrite the story of how worlds and comets form. Consider the chemistry. Most comets in our solar system are dominated by water. Carbon dioxide and carbon monoxide play supporting roles, never the lead. Yet Atlas is different. CO2 surges 8 times stronger than water, producing a coma larger than the Earth-Moon distance. If this is natural, it suggests that planetary systems can produce comets with radically different balances of volatiles. Our Sun's nursery is not the template, it is just one variation among many. Somewhere out there, under colder stars or in stranger disks, comets like Atlas may be the norm. Then there is the nickel. Its presence without iron unsettles expectations, but even if this proves to be a quirk of excitation or detection, it reminds us how much we still do not understand about the chemistry of ejected worlds. Nickel lines shining in Atlas's spectrum may tell us about the environments in which it condensed, environments with conditions unfamiliar to us. It is a clue, not of design, but of diversity. Its trajectory, too, carries lessons. If natural, then Atlas is a dart thrown across the galaxy, a shard ejected by gravitational chaos in a distant system. That it happened to pass near Mars, vanish behind the Sun, and sweep past Jupiter may be coincidence. But coincidence or not, it shows us that interstellar wanderers will continue to arrive, drawn by no plan but their own inertia. To study them is to study fragments of alien systems delivered to our doorstep. Even the anomalies, the forward glow, the early water, the sulfur clue, may be windows into natural processes we have yet to model. Every comet surprises us. Atlas simply surprises us more. If its story is natural, then it is telling us the cosmos is more inventive than we imagined, capable of sculpting wanderers that defy our categories. In that sense, calling it just a comet undersells the gift it brings. Atlas is a messenger. Its chemistry expands our understanding of planetary nurseries. Its dust reveals scattering behaviors unknown in local comets. Its gas flows challenge our thermal models. Every anomaly, natural or otherwise, becomes a lesson. So if Atlas is only a comet, then it is still extraordinary. It is proof that the galaxy holds more diversity than we can grasp. It is a reminder that knowledge itself is wonder, and it is a gift, a piece of another star's history, placed within reach for a fleeting moment before it drifts back into the dark. But if not, if this is design, intent, or message, then the worst, or perhaps the most extraordinary, is still to come. To imagine 3i Atlas as more than a comet is to step into speculation, but speculation has always been a shadow companion to science. If its anomalies are not natural, if the nickel without iron, the forward glow, the immense CO2 bubble, and the rhythmic light curves all hint at design, then we are not observing debris, we are watching a craft, And if it is a craft, then the questions multiply. What is its purpose? A probe, perhaps, sent from a distant civilization to study planetary systems across the galaxy. A surveyor, gathering data silently as it glides past Mars, hides behind the Sun, and tests Jupiter's immense gravity. To us, the path may feel like coincidence. To a designer, it may be choreography, each step a deliberate choice. Or perhaps it is more than a probe. If it is engineered, then Atlas could be a message, drifting slowly until chance delivers it to an inhabited system. Its anomalies, too strange to ignore yet subtle enough to deny, could be a kind of code. A puzzle meant to provoke the one question we fear to ask. Are we alone? If so, then its mission is not surveillance, but communication, carried out not through signals but through its very existence. And yet, darker possibilities linger. In the framework of the dark forest scenario, a disguised probe may not be here to talk. It may be here to watch, to measure, perhaps even to decide. To hide behind the Sun at perihelion is to act without witnesses. To swing by Jupiter is to harness gravity for a slingshot maneuver, perhaps toward another destination, perhaps deeper into the solar system itself. If this is not a comet, then its intent could be unknowable and not necessarily benign. But intent is difficult to measure from afar. To call it a craft is already a leap, to ascribe motives is another. Still, the possibility transforms Atlas from curiosity into omen. If designed, then it is evidence that intelligence exists elsewhere, and that it has reached us first, silently, without fanfare, cloaked in dust and gas. Some would call this the most extraordinary event in human history, proof that we are not alone, delivered not by radio signal but by rock and ice shaped into disguise. Others would call it the worst. A reminder that survival may depend on silence, and that discovery is not always a gift. For now, Atlas remains undecided. Its coma glows, its orbit unfolds, and we are left to wonder. If it is a comet, it expands our science. If it is not, it expands our reality. And in that distinction lies the line between comfort and awe, between safety and danger. If it is not just a comet, then its story is only beginning, and we, standing on the shores of one small world, may already be part of its script. We have walked together through the questions raised by 3I Atlas, its unusual chemistry, its puzzling trajectory, and the silence that surrounds it. We have asked whether it is simply a comet, rewriting what we know of planetary formation, or whether it might be something more, a seed, a machine, perhaps even a message. The title posed the big question: is the worst still to come? But perhaps the truth is not about worst at all. Perhaps it is about perspective. If Atlas is only a comet, then it is a remarkable one, carrying lessons that deepen our science. If it is not, then it expands our sense of what is possible in a universe far larger than our current understanding. Either way, it is not a threat, it is an opportunity. An opportunity to wonder, to question, and to remember that our place in the cosmos is both small and extraordinary. So as this story closes, take comfort in knowing that mystery itself is a gift. We do not need all the answers to feel grateful for the privilege of being here, alive at a time when such discoveries unfold before us. Rest now with that thought. Whether Atlas is comet or craft, the universe remains vast, rich, and endlessly surprising. And in that wonder, there is peace.